Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Let us take up now an example of 2D heat conduction, which we have been discussing in the last 2 lectures. In this, so we have a square plate of 2 by 2. Sides are two units. And then for simplicity, let us take conductivity as 1. Heat source is there, Q is equal to 1. And then there are boundary conditions. So these all sides are exposed to a temperature of 0. Okay. So that means that all sides are gamma phi type of boundary condition, right? Gamma, all sides are gamma phi. Okay. Phi bar is 0 and everywhere it is 0. So this is fine. So this is the geometry and the material and the boundary conditions. So if you look at that again, this is a symmetric problem. So it's a square plate with material, of course, being constant thermal conductivity, and Q, the heat source, and the boundary conditions, they are all symmetric about X and Y axis. So if so, then what we need to take into consideration is good enough if we take only 1 quarter plate. So that means that this quarter plate, if you take it, so geometry, material, and boundary conditions are all symmetric. So that means that solution is also symmetric. Okay. So that means that we can consider symmetry about X and Y axis. So that means that take only X and Y axis like this, right? So here you can see that the top face is maintained at a temperature of 0. The right side edge is also maintained at a temperature of 0. And what about these sides here? So the sides, bottom and the left side. So since obviously they're symmetric, so that means that temperature we are not prescribing because we do not know. And however, the heat conduction here, heat flux here, which we call as Q bar, has to be 0. So that means that heat neither goes this way or goes the other side, right? It neither goes this way or that way. So Q bar has to be 0, right? And similarly on this side also, the heat leaving the surface is 0. So it's a symmetric thing. And so that means that now the originally gamma, it's all gamma phi boundary conditions. Now we have gamma Q boundary condition on 2 sides. Okay. Further, if you also consider the diagonal here, if you consider the diagonal, so then again the problem is symmetric about, you can see about diagonal. Okay, so you can see that the whole thing is symmetric about the diagonal. So we can even consider only one half of the plate, one this triangular piece here as, I'll just draw it bigger here. Okay, so this is the origin here, and here we have q bar 0 and I bar 0 here, and again because it is a symmetric thing, again no heat is leaving or entering, right? So q bar is 0 on the diagonal. Heat neither enters nor leaves, right? So q bar is 0 on the diagonal here. So we made the problem as simple as possible. So that means that what it means is that if you can solve the temperature field for this one, okay, if you can solve for this one, so then this will be symmetric, and then the whole thing can be taken a mirror image here, and the whole thing can be taken as a mirror image about the x-axis. So like that, so this is simplified to this extent. And now the discretization. So we'll discretize this using triangular elements. Of course, that's what we have done so far. And let's, instead, we cannot afford to take only one element. So let us take just a few more elements like this one. So there are 4 elements. All are of equal size except that this is turned upside down. So let us just take the so let's put the nodes at these points, and let's call this as 1, 2, 3, 4, 5, 6. So these are the 6 nodes and 4 elements. 1, 2, 3, 4 elements. Okay, there are 4 elements and 6 nodes, and we know exactly the coordinates. So the coordinates are known here. So this is 0, 0, and this is 1, 0, and this is 1, 1. And other intermediate nodes coordinates also we can find out. This is nothing but 0.50. This is 0.5, 0.5, and this is 1.5. So coordinates are easy to find out. The other important thing here is the connectivity. So connectivity will give you the element numbering and the node numbers. So the element number and nodes here. we call them as I, J, K. One, two, three, 4. And the elements are 1, 2, 3 for the first element. And second element, we'll put it as 5, 3, 2. And the third element is 2, 4, 5. And fourth element is 3, 5, 6. We kept the orientation of the element as well as the size. So exactly similar. For example, 1, 2, 3 and 2, 4, 5 as well as 3, 5, 6 are same. Except that I took this 5, 3, 2. I know that it's from the reverse side. But well, I know that its difference matrix will be same. So that's why I took it that way. All right. So now what we need is the finding out of the elemental matrices and then assembly. Okay. So we go by element. So we'll take element number 1, where I is 1, J is 2, K is 3, and the coordinates are 0, 0 and 0.5, 0 and 0.5. Okay, so after this, so these are all just calculations here. One is the BI. You calculate. BI has been given as to be Yj minus Yk by twice area. In fact, area here is nothing but half 0.5 is 1 by 8. This is what is needed, and then I'll just write down these things. Bi is minus 0.5 by 2a, and Bj is 0.5 by 2a is the determinant, and Bk is 0. And so similarly, we can find out Ci 0 and Cj is minus 0.5 to A. Okay, so these are Bi, Bj, Bk, Ci, Cj, Ck. And what, right? We have the K matrix, and then you substitute that. For the element, the K matrix, we know what it is. I'll write it down all the same. Bi square, A square, Bi, Bj, in fact, you can also observe that this matrix is symmetric. It's a symmetric matrix. So if you substitute this, there's a K here, there's a element A here. What is this? A has come because of the integration. Okay. So this K for this element k being 1 and so on. So we get 1 by 24, 1 minus 1, 0. This is how it looks to be, right? Okay. Substitute all those values. This is what you get. On the other hand, on the right side, if you call it as f vector, okay, consists of 2a by 3, 2a by 3. This is for the element. And this will turn out to be, sorry, this is not 24. This is 1 by 2. Actually, this comes out to be 1 by 24, 1, 1, 1. Okay. So this is this is because of the right side vector, which is coming because of the heat source Q. There is also another term which comes. The second thing which will come is because of the heat flux. And here it so happens heat flux anyway on these two boundaries, it's anyway 0, so it doesn't contribute anything at this point for this problem, right? So like this, so we can find out the others also. Interestingly, so the others also will come out to be for, you can calculate 1 by 1. So for element 2, so the I is 5, J is 3, and K is 2. And it turns out to be K exactly same as this one. Please, you can verify this one. In fact, all the matrices for all the elements, it turns out to be same. Okay. IJK is 532 and element 3 is 245. And again, K, I'm just writing it. Okay, and so similarly here, F also will turn out to be same. And element 4. So why I'm writing this thing is that this IJK are different. Right? So K happens to be exactly same. K1, if you want, I'll write it 4, and this as 3, and this as 2, and this as 1. Okay. Okay, so I wrote all these things repeatedly for one reason. Now we have to assemble this, all these elemental matrices into the system matrices. So the system matrix K, you want, will turn out to be a big matrix Okay, so the system matrix will consist of all the nodes. So they are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. So the first element here is in the nodes 1, 2, 3. 1, 2, 3 here, right? So these go to the appropriate place here. So they will go to the node 1, 2, 3 will go to 1, 1, 1, 2, 1, 3. So that means that they go like this one here. So this is 1, minus 1 and 0 here, and minus 1, 2 here, minus 1. Okay, so this is for the first element, and then we can do it for the second element. Second element has 5, 3, 2. 5, 3, 2. 5, 3, 2. Okay, so that means that this one will go to 5, 5. So 5, 5 is here, and 5, 3 is minus 1. So this 5, 3 is minus 1. And then we have this is 5, 5, 5, 3, and this is 3, 5. So 3, 5 is here, minus 1, and 3, 3 is 2. So at 3, 3, you have to have 2 here, and then 3, 2 is minus 1 here. Okay, and then the last one is 2, 3 is minus 1, 2, 3 is minus 1, and 2, 2 is 1. So like this, so these white marked things are the thing. And then similarly here, for the element 3, it goes to 2, 4, 5. So 2, 4, 5. So this is 2, 4, 5. That means 2, 2 will have a 1 here, and 2, 4 will have a 1, and 5 is not having anything. And 4, 2 has minus 1, and 4, 4 is plus 2, and 4, 5 is minus 1, like this. And then you have 5, 4 is minus 1, and 5, 5 is plus 1. Okay, so like this you have, and then finally you have 3, 5, 6 here. So in the 3, 5, 6 you have 3, 3 as 1 here, and 3, 5 is minus 1, and then 5, 3 is minus 1, and 5, 5 is 2, and 5, 6 is minus 1. Then you have 6, 5 is minus 1, and 6, 6 is 1. So like this you have all the elemental matrices are substituted into the system matrices. Apart from this, we also have the F vector here. So 1, 2, 3, 4, 5, and 6. So this F also has to go appropriately into, say this is 1, 2, 3. Of course, this 1 by 24 is there. 1, 2, 3. So it's 1, 1, 1. And this goes to 5, 3, 2. 1 and 1 here, and this goes to 2, 4, 5, 2, 4, 5, and finally it goes to 3, 5, 6, 3, 5, 6 here. So like this, so the F vector is also assembled appropriately. Now, so the final set of equation looks like this. So it is K times phi so where we will put down here, of course there is a half here, forgot. Simplifying this equation, this is easy, 1, 3, 3, 1, 3, 1, and here this is 1 minus 1, 0, 0, 0, minus 1, 4, 2, minus 1, 0, 0, and 0 minus 2, 4, 0 minus 2, 0, 0 minus 1, 0, 2 minus 1, 0, 0, 0 minus 2, minus 1, 4 minus 1, 0, 0, 0, 0, minus 1, 1. Okay, so this is the final set of equations in the matrix form, and then this now is K multiplied by the temperature values at the 6 nodes which are to be solved, and then this is the heat source here. So one thing that's done, as you recall, the boundary conditions are given on node 4 and 5 and 6. For example, this 4, 5 and 6 have been given to be 0. Okay, these are given 0. So now these are simple 0. Now the question is that there are 6 equations here, and we have to solve for how many? 3 unknowns, right? Which are the 3 unknowns? Phi 1 and phi 2 and phi 3. So the question now is that which you can choose any 3 equations and solve for the 3 unknowns, right? So but however, you cannot really take any 3 equations. There are some constraints in this one. How are these equations obtained? If you look at the way the equations have been obtained, how is this first equation obtained? The first equation, if you recall, so as such, I'll write, you can choose 3 equations. So which 3 equations which you have to choose? So that is the point of discussion. So that means that the first equation, if you recall, has been obtained by taking the weighting function Wi is equal to N1, right? So this is 1, 2, 3. 1, 2, 3, 3, 4, 5, 6. Obtained by taking Wi is equal to N1. So what is N1? N1 has a value of 1 and goes to 0, something like here, and goes to 0 and something like this. So this equation is okay. Why? Because it has to be Wi has to be 0 on gamma phi. So this is gamma phi. This has to be the gamma phi, and then you have to choose, you can choose this N1. In particular, can you choose Wi is equal to N4? Can you choose Wi is equal to N4 or N5 or N6? This is not acceptable to us, because if you choose Wi is equal to N4, then N4 we know very well that N4 has a value of 1, okay, here, value of 1, and then goes to 0 here and goes to 0 on this side, right? That's fine enough. But on this side, gamma phi, N4 is not 0. N4 is non-zero on gamma phi. So N4 is non-zero on gamma phi. So this equation cannot be used. So similarly, we cannot use Wi is equal to N5 and N6 cannot be used. Only Wi that can be used satisfactory is Wi is equal to N1 is fine. Wi is equal to N2 is also fine, because you have a value of 1 here and goes to 0. That's fine enough. Even Wi is equal to N3 is also acceptable, because it goes to 0 at this point. So that way, the valid equations we can choose are equations 1, 2, and 3, the first 3 equations. So that means that, how is that? Only first 3 equations can be chosen. So we can, in fact, we can 1, 4, minus 2, right? And 0, minus 2, 4. So we are going to partition this one like this one, phi 1, phi 2, phi 3. We are partitioning the matrix so we'll choose 0, 0, 0 and minus 1, 0 and 0, minus 2, 0 times phi 4, phi 5 and phi 6. So this is equal to 1 by 24 on the right side is 1, 3, 3. So this can be, knowing these phi 4, phi 5 and phi 6 being 0 here, phi 4 and phi 5 and phi 6 are given to be 0 in this particular problem. Otherwise, if it is non-zero, also you can take that. Maybe if it is 100 degrees, you can take it 100 and multiply it and take it to the right side. Then solving for phi 1, phi 2, phi 3. So that means that phi 1, phi 2, phi 3, we can solve it by taking the inversion of this one. 1 minus 1, 0, minus 1, 4, minus 2, minus 1, invert, and 1, 3, 3. So if you solve for this one, so the answer you get 0.1354, 0.938, 0.573. Okay, so this is the solution. Now I hope you have followed every bit of it. It's very important, particularly so which equation to choose is very important here. So if these essentially, if these things are prescribed, so you cannot really use these things because these are obtained by using Wi is equal to n4, n5, n6, which is not valid, or which is not valid to use the weighting functions here because they had to be 0 on comma 5. So I hope you have followed this. So this is a very typical procedure of finite element analysis. So you have to make a choice of the element, you have to discretize the system, and then you have to give the node numbers and element and connectivity, find out the element stiffness matrices, element F matrix, and then find out the assembled matrix and put it here and apply the boundary conditions appropriately. So in the next class, we will take up the solid mechanics application, and so that will be a little bit more involved because the number of variables will be one more. So there are 2 variables in that, and we will take it up once you know this. So following that will not be that difficult. So we'll stop here. Bye.